Hello everyone, welcome back to coinslive. Today we are solving LeetCode problem number 560, subarray sum equals k. The problem says we are given an integer array nums and integer k. We need to return the total number of subarrays whose sum is exactly equal to k. And remember, a subarray must be contiguous. For example, array is 1 1 1 and k is equal to 2. There are two valid subarrays, that is first subarray is indices 0 to 1 and in indices 1 to 2, this subarray. These two subarrays sum is equal to 2, so the answer is 2. At first this problem may look like a sliding window problem, but there is one more important catch. The array can contain negative numbers, and because of that the normal sliding window approach will not work reliably. The optimal solution uses prefix sum plus HashMap. Let's understand why. The simplest approach is to generate every possible subarray. Suppose we have, so this is our array and k is equal to 3. So we will calculate using nested loops all the subarrays, and the possible subarrays are 1, 1, 2, 1, 2, 3, 2, 2, 3 and 3. So these are the possible subarrays. Now we will calculate their sums. This first subarray will equal to 1. This subarray will equal to 1 plus 2 3, and this subarray sum will be 6, and this will be equal to 2. This will be equal to 5, and this will be equal to 3. Now we will see that which sum is equal to our k, 3 and 3. There are two sum that is equal to our k, so the answer is 2. So the outer loop selects the starting index and inner loop keeps extending the subarray. So this is the brute force approach that we can use. So for brute force code, this will look like this. We will initialize a counter and define a loop. So the outer loop finds the starting index. It selects the starting index, and the inner loop keeps extending the array and keep counting the current sum. When when the current sum is equal to k, the count will be increased and we will return the count. This works, but what is the time complexity? It is the outer loop running n times, and for each index the inner loop can also run almost n times. So the time complexity is big of n square. Given that nums given that the length can be around 20,000, this can become too slow. We need something better. A natural thought might be, can we maintain a window and adjust its size depending on the sum? This works in many subarray sum problems when all numbers are positive. For example, 1, 2, 3, 4. If the sum might, uh, if the sum becomes too large, shrinking the window always reduces the sum. But here, numbers can be negative. Suppose 2 minus 1, 2. So adding another number might increase the sum or it might decrease the sum, right? Similarly, removing a number might increase or decrease the sum. Therefore, we cannot reliably decide that if the sum is too large, then we should move left, or if the sum is too small, we can know right. So sliding window is not suitable. Instead, we need to think in terms of prefix sum. A prefix sum means the sum of all elements from the beginning of the array up to the current position. Suppose, so at zeroth index, the element is 1, so the prefix sum will be 1. In the first index, the element is 2, so the prefix sum will be 2 plus 1, that is 3. Now at the second index, that is element 3, the prefix sum will be 3 plus 3, 6. So we get 1, 3, 6. Now suppose the current prefix sum is 6 and we want a subarray with sum 3. If an earlier prefix sum was also 3, then 6 minus 3 is equal to 3. This means the elements between those two prefix sums have sum equal to 3. That is, this element 3 will be the subarray. Now for this, at this instance, think that this index is I and this index is j. Suppose our current prefix is the sum from 0 to index j. Sum from index 0 to j. So the current prefix sum is equal to 6, this, and previous prefix is equal to the sum of index 0 to I. Then the subarray after I and up to j has sum 3, that is current prefix minus previous prefix. So the current prefix sum is equal to 6 and previous prefix sum is 3. We want that value to be equal to k, and if we rearrange this formula, we will get previous prefix equal to current prefix minus k. So this is the entire idea of the problem. At every position, once we calculate our current prefix sum, we ask, have we seen current prefix minus k before? If yes, then we have found a valid subarray ending at the current position. Suppose in this index, we saw that our current prefix sum is 6. So we will ask we will ask that if 6 minus k, that is 3, if we have 3 seen before, yes, we have seen before at index I, that is index 1. So this will be our idea to find the subarray. Now let's uh, take one example and understand the whole idea. So this is our array and our k value is equal to 3. We are finding those subarrays that sum is equal to 3. Now initially the prefix sum is 0. At 0th index, the prefix sum is equal to 1. The element is 1. So the prefix sum is not equal to k. Now we will move further. In the index 1, the value of prefix sum will be 2 plus 1, that is 3. So we find that prefix sum 3 is equal to our k value, right? So we will increase the count. Now the second index, the prefix sum value will be 3 plus 3, that is 6. Now we will ask that 6 minus k, that is 6 minus 3 is equal to 3. So do we have earlier prefix sum 3? So we have seen the 3 prefix sum in the previous index. Yes. So this subarray is our the first subarray, right? Now the second subarray 6 minus 3 will be this. So we will increase the count. So what we did, we asked that do we have 3 before? Yes, we have 3 before. So we increase the count. Now we move further in the index 3. The prefix sum is 6 minus 3, that is 3. So we have found 3 again. Now we will see that this subarray equals sum 3. 1 plus 2, that is 3. 3 plus 3, that is 6. 6 minus 3, 3. So this subarray will our also an answer. So the question is, uh, how do we find how do we find that this is our another subarray? So initially I had a prefix sum equal to 0. We will ask that our current prefix, that is 3. 3 minus 3 is 0. So do we have seen 0 before? So yes, 0 was before initially. So we will increase our count. So in this position we have to uh, insert a value, that is prefix sum is equal to 0 for another index, that is let's say -1. Now at the next index the prefix sum will become 4. Now ask that 4 minus k, that the current prefix minus k, 4 minus 3 is equal to 1. So we have seen before. Do we have seen before? Yes, 1 we have seen before. So we will increase the count. Now at the next index 4 plus 1 is 5. So 5 minus 3 is equal to 2. So do we have seen 2 before? No. Any prefix sum is not 2. Now at the next index 6. So 6 minus k, that is 3. And do we have 3 do we have seen 3 before? Yes, in this uh, we have uh, we have seen 3 two times. So this subarray and this subarray also equal to 3, right? So how do we tackle that? So kept we will keep the frequencies of the prefix sum in a hash map. So in the hash map we will keep the prefix sum and the frequencies of the same. So we have the frequency of the prefix sum 3 is 2. So we will increase the count to plus 2, that is 6, right? And the next index, that is 4. 6 plus 4 is equal to 10. So 10 minus 3, that is 7. Do we have seen 7 before? No. Now 10 plus 2 is 12. So do we have seen 12 minus 3, that is 9 before? No. Now 9 minus 3 is equal to 6. So 6 minus 3 is equal to 3. So do we have seen 3 before? Yes, 2 times. So the prefix sum will be um, so the count will be 6 plus 2, 8. So this will be our run process. So why do we start with 0 minus 1? This is a very important detail. Suppose the array contains 1 comma 2 and k is equal to 3. After processing both elements, current sum is equal to 3. We calculate current sum minus k, that is 3 minus 3 is equal to 0. This means the entire sub array from 0 to index to the current index has sum is equal to k, but there was no actual prefix sum before index 0, right? Conceptually, before processing the array, our prefix sum was 0. So we initialize prefix count 0, that is frequency is 1. This allows us to currently count subarrays that begin at index 0. So why do we store frequencies? You might wonder, why not simply store prefix sum in a set? Why do we need to why do we need a dictionary containing frequencies? Because the same prefix can appear multiple times. As we seen before, 3 came twice, right? And every occurrence can represent a different valid subarray. Like we seen that there were two subarrays, this and this. So for that purpose, we need to store frequencies of the prefix sum. If a prefix sum has appeared multiple times, we need to count all those occurrences. That is why we store prefix sum and number of occurrences rather than simply whether it exists. There is one subtle implementation detail. For each number, we should first update current sum, check current sum minus k, add the answer, then store current sum in the map. Why do we check before storing the current sum? Because the prefix sum we are searching for should come from an earlier position. We do not want to accidentally use the current prefix sum as its own previous prefix, so the order matters. So our pseudocode will look like this. We will create a hash map and we will insert an element prefix count 0 with frequency 1, and current sum will be equal to 0 and count will be equal to 0, and we will use a loop for each number in nums. We will add a number, we'll add the number to current sum, and we will calculate current sum minus k, and if it exists in the prefix count, we will add its frequency to the count and increase the frequency of current sum. Now we will return count. Let's convert this directly into Python. We inserted the first element. This dictionary stores the frequency of every prefix sum we have seen. We start with prefix sum 0 occurring once. Then initializing these two variables, current sum stores our running prefix sum and count stores the number of valid subarrays. Now we process every element and add it to the previous sum. Now we calculate the prefix sum that we need to have seen earlier. If this value exists, then every occurrence represents one valid subarray. So finally record the current prefix sum, and after processing the entire array, return the count. Let's also dry run. So initially prefix count is 0 and the occurrence is 1, and the current sum is 0, count is equal to 0. Now process 1, current sum is equal to 1, and what is needed 1 minus 3, that is minus 2. Minus 2 does not exist. Now let's store 1 in the dictionary. Our first element was this, and the second element is this, right? Now process 2, now current sum is equal to 3, and 3 minus 3, that is 0, and 0 exists once, so the count will become 1. That represents this subarray. So store 3 with occurrence 1. Now process this element 3. Current sum is 3 plus 3 is 6. Now what is needed? 6 minus 3, that is 3, and prefix sum 3 exists 1. So the count will be 2. This represents this subarray. So the final answer is 2. Let's run it once. Now let's do complexity analysis. We iterated through the entire array exactly once. For every element, hash map lookup and insertion are big of 1 on average. Therefore, the time complexity is big of n. For space, in the worst case, every prefix sum is different. So the dictionary can contain up to n plus 1 values. Therefore, space complexity will be big O of n. Now let's discuss some common mistakes. The first common mistake is trying to use sliding window. Sliding window usually works when the numbers are positive because increasing and decreasing the window changes the sum predictably. Here we can have negative numbers, so sliding window does not reliably work. Another common mistake is starting with prefix count empty instead of prefix count 0 for occurrence 1. If you do this, you will fail to count valid subarrays starting at index 0. Now, the third mistake, using a set. Do not use a set because because the same prefix sum can appear multiple times. We need to know how many times it appeared. So, use a frequency dictionary. This problem teaches a very useful DSA pattern. Whenever a pattern says something like count the number of subarrays with sum equal to k, you should immediately think about prefix sum plus hash map. The key equation we discussed before, this current prefix minus previous prefix equal to k, and which becomes previous prefix equal to current prefix minus k. So at every position look for current prefix minus k. Now let's quickly recap. We need to count contiguous subarrays whose sum equal to k. Brute force takes n square time. Sliding window cannot be reliably used because negative values are allowed. Instead, we maintain a running prefix sum. At each index, we ask, have I previously seen current sum minus k? If yes, then each occurrence gives us one valid subarray ending at the current position. We store the frequency of previous sums using a hash map, and that gives us time complexity of big O of n and space complexity of big O of n. The one formula you should remember from this problem is current prefix minus previous prefix sum is equal to k. Therefore, previous prefix is equal to current prefix minus k, and that's the complete solution to LeetCode 560 subarray sum equals k. I will see you in the next video.